Alright guys, so today in our problem, we're going to have two different types of coins in your pocket. One type of coin is going to be fair. Now the fair coin, as you can see, on one side is tails and the other side is heads, like a normal coin. And the other type of coin we have is an unfair coin. This type of coin is heads on both sides, so two-headed coin. So in your pocket you're going to have both types of these coins. So in your pocket you're going to reach and you can go and pick one coin out at random. Alright. Let F be the event that the coin you picked is fair. So F is for fair. Let F bar, which is the complement to F, be the event that the coin you picked is unfair. So you reach into your pocket and you pulled out either a fair coin, F, or you pulled out an unfair coin, F bar. The sample space, or the set of all possible outcomes, is given in this diagram right here. Since F and F bar are mutually exclusive, you can only pick out one coin. It's either going to be fair or unfair. And since the union of F and F bar, which is F's complement, unfair coin, is the entire sample space, we can say that F and F bar partition the sample space, omega. So what is the problem that we're given? The problem is that in your pocket you have M fair coins and N two-headed unfair coins. You pick one coin out at random, and without looking at it, so you don't know which coin it is, you flip this coin K times. You observe the outcomes. Let H sub I be the event that you get a head on the ith flip. So H sub 1 is that you get heads on the first flip, H sub 2 you get heads on the second flip, and so on. And let E sub K be the event that you flip K heads in a row. For instance, we have it described here mathematically. E sub K is the intersection of H1, H2, H3, intersected all the way up to HK. So E sub 4, for instance, is the event that you get heads on the first try, and then you get heads on the second try, you get heads on the third try, and you get heads on the fourth try. So the problem that we have to answer are, what are the smallest M and N such that, number one, the probability that you have a fair coin, given that you see two heads in a row, is equal to 1/5. Number two, the probability that you have a fair coin, given that you see a heads on the first try, is equal to 1/2. Number three, that the probability of having a fair coin, given that you see two straight heads, is 1/2. And number four, that the probability of having a fair coin, given that you see three straight heads, is 1/6.
Okay, now that our problem has been set up, let's get our basics right. Let's assume that P of F is the probability that you picked a fair coin, and P of F bar, or P of F complement, is the probability that you picked the unfair coin. Now, by crude counting, the probability that you pick the fair coin can be given as the number of fair coins in your pocket divided by the total number of coins. That comes out to be M by M plus N. Applying the same logic, the probability of choosing an unfair coin is going to be N by M plus N. Now, if you add both of these probabilities, it's going to be equal to 1. So, what does that say? That says that both F and F complement are mutually exclusive. So that can be written as P of F complement is equals to 1 minus P of F. Now let us talk about conditional probability. Let us consider this Venn diagram where A and B are two events in a sample space omega, and both are not mutually exclusive apparently from this diagram, and P of A by B, or as you know, P of A given B, is defined as the probability of A occurring given that B has occurred. This is conditioning on B. So this can also be represented in the Venn diagram form as follows. P of A given B then is equals to the probability that A and B both have occurred divided by the probability that B has occurred. From this, by rearranging these terms, we get that the probability of A intersection B, or the probability that both A and B has occurred, is equals to the probability of A occurring given B multiplied by the probability of B. Applying this concept of conditional probability to the problem where we need to find the probability of a fair coin being chosen given that the event Ek, which is k heads occurring on a row given the coin is flipped k times, can be written as P of f given Ek is equals to P of both the fair coin being chosen and Ek occurring divided by P of Ek. Now, how do we calculate the probability of k heads occurring on a row given the coin is also flipped k times? Now, that can be found out using the law of total probability. Now, we know that our sample space is omega, and f and f complement are the two mutually exclusive events defined on the sample space. That means the sum of their probabilities is going to be 1. And Ek is the event that we are trying to find out the probability of. Now, what the law of total probability gives us is P of Ek is equals to P of Ek given f times P of f plus P of Ek given f complement times P of f complement. Now, the law of total probability can be explained from this example where we have a sample space omega which has partitions A1 to A8. The B is the event occurring in the sample space omega, and B can be written as B is equals to B intersection A1 union B intersection A2 and so on union B intersection A8. Now, from the conditional probability we have derived earlier, P of B is the summation of probability of B occurring given AI times P AI from I equals to 1 to 8, which is the total number of partitions we have. Now, extending that law of total probability and the conditional probability to our conditions, this equation, the numerator, can be rewritten as, instead of P of f intersection Ek, it can be written as Ek intersection f. Both are the same things, you're just writing them in a different order. But applying the law of conditional probability to this, it can be written as P of Ek intersection f divided by P of f, which we have just derived, conditional probability. By rearranging these terms, we arrive at P of Ek intersection f is equals to P of Ek given f times P of f. From equations 1, 2 and 3, we arrive at this equation where you can get probability of choosing a fair coin given the event Ek has occurred is equals to probability of event Ek occurring given a fair coin is being chosen times probability of the fair coin being chosen divided by the total probability of Ek occurred. This is also known as the Bayes rule. Bayes rule is a very important tool in probability. It helps us to calculate the a posteriori probabilities from a priori probabilities. A posteriori probabilities are the probabilities of the input occurring after measuring the output, and the a priori probabilities are the probabilities of your input occurring.
So from our earlier calculations, we found out that probability of picking a fair coin is equal to m by m plus n, and similarly probability of picking an unfair coin is equal to n by n plus n. So once we pick a fair coin, we can see that from our intuition or by calculating the sample space that probability of picking a heads of getting a heads on our trial is equal to 1 by 2. Since we have two outcomes in our sample space, that is a heads or a tails, and we want a heads, so the probability of getting a heads on a fair coin is equal to 1 by 2. And similarly, probability of getting a heads on k consecutive trials is equal to probability of getting probability of h1 intersection h2 intersection till hk. given that we pick the fair coin is equal to 1 by 2 into 1 by 2 into 1 by 2 until we k times. So it's basically 1 by 2 to the power k. And similarly, once we pick an unfair coin, we know that both the outcomes are heads. So the probability of getting a heads on any of our trials is 1. So now we have the probability of getting a heads on both, given that we picked a fair or an unfair coin. So we had talked earlier about Bayes' theorem, which gives us this equation that probability of picking a fair coin given we got k consecutive heads, or the event ek has occurred, is equal to probability of ek occurring given that fair coin was picked multiplied by probability of picking a fair coin divided by probability of ek occurring, which is given by the law of total probability and written over here. So now substituting all our values that we had derived earlier, we get this form, which is basically m by m plus 2 raised to the power k into n. So this is the probability that a fair coin is picked given that our event ek has occurred. So the first part says that is the probability of picking a fair coin given that our event E2 has occurred, or 2 consecutive heads have occurred, is equal to 1 by 5. And we basically have to calculate the number of unfair and fair coins required, minimum number of unfair and fair coins required for this particular case. So solving this equation, we get that m is equal to n. And in order to get the minimum number of coins, we select both of them to be 1. So if we have one fair and one unfair coin, we get this probability to be 1 by 5. And similarly, probability of getting a fair coin given that one head has already occurred is equal to, H1 is basically equal to the event E1 where one head has occurred. So P of F given E1 is equal to 1 by 2 is what we are given in the question. Again, substituting the values, we solve this for the solve this and we get the equation m is equal to 2n. So again, in order to get the minimum number of coins, we select n to be 1, and which gives us that m is equal to 2. So basically we require 2 fair coins and 1 unfair coin to get this particular probability. Now moving on to the third part, which is again similar, gives us the probability that of us picking up fair coin given that 2 heads have occurred is equal to half. Again, substituting the values, we get the equation m is equal to 4n. So once we substitute the value of n to be 1, we get m is equal to 4. So again, if we have 4 fair coins and 1 unfair coin, we get this particular probability. The fourth and the last part is also similar to the earlier parts, which basically asks us the probability of picking a fair coin given that 3 consecutive heads have occurred. And the probability given to us is 1 by 6th. So again, substituting the values, and we get the equation to be m is equal to 8 by 5 into n. So in order to get our required probability, the least number of coins we require is 13, out of which we need 8 fair coins and 5 unfair coins. So that was our problem. Thank you.